I'm going to look at some exam style questions. This is for the topic of orbits and satellites. The first question I'm going to look at a low Earth orbit satellite. And as I discussed in a previous video, they're between 300 kilometers and 2,000 kilometers above the Earth. And then this example is looking at the International Space Station. So it says the International Space Station is an artificial satellite in low Earth orbit. The ISS has a mass of 4.19 times 10 to the 5 kilograms and orbits at a height of 4.1 times 10 to the 5 meters above the surface of the Earth. One thing to note that sometimes these questions talk about a specific height above the Earth, but when we're looking at orbits, we need to know the radius of the orbit from the center of the planet. So we'd need to know what the radius of the planet is if we're given the height. So the radius of the orbit would be the height of the planet, the height above the planet plus the radius of the planet. So just one thing to bear in mind. It says the radius of the Earth is 6.37 times 10 to the 6 meters, and the mass of the Earth is 5.98 times 10 to the 24 kilograms. Calculate the time taken for the ISS to complete one orbit of the Earth. Okay, so in other words, one orbit would be, or the time taken for one orbit is the time period. And in the video on theory, we came up with this expression. Okay, so what this is suggesting is that the time period is dependent upon how far away from the centre of the planet is and the size of the planet, and then 4 pi squared over g, it's all constant. Okay, now r, remember, we mean radius of planet Earth plus the height it orbits above the Earth. And then we can calculate that because we know that the radius of the planet given here is 6.37 times 10 to the 6 meters. And we're going to add to that the height of the orbit above the planet, times 10 to the 5 meters. And if we calculate that, it comes out as 6.78 times 10 to the 6 meters. So that's what our radius for the orbit is. Then the other numbers, we've got the mass of the Earth, that's big M, and then the gravitational constant G, that is 6.67 times 10 to the minus 11. And then that's in newtons meter squared per kilogram squared. Right, let's plug all these numbers into this. So the time period would equal 4 times pi squared times 6.78 times 10 to the 6. Now we're going to cube that, divided by 6.67 times 10 to the minus 11 times 6. No, sorry, I was going to round this up to 6, but we'll go with what they give, 5.98 times 10 to the 24 kilograms. And then we're going to square root all of that. So the thing to note is that you have squares, cubes, square roots. Don't forget to do these things, otherwise you're not going to get the correct calculation. This comes out then at about 5,500 seconds. Okay. And if we divide that by 60 in minutes, that's 92 minutes. Okay, so the time taken, the time period is 92 minutes. Okay, so it orbits the planet every 92 minutes, and in a 24-hour period, so in a day, I think it orbits about 16 times, just under 16 times a day. Next question. Calculate the gravitational field strength exerted by the Earth at this height. Okay, so what we're suggesting is that the satellite above the Earth, or orbiting it at a radius of 6.78 times 10 to the 6 meters, this will, within the gravitational field that far away, G will equal gm over r squared. Okay, so again, don't need to discuss why. Field strength is the force per unit mass, and so in terms of big G, it's gm over r squared, and we've done that before in previous videos. So let's just plug numbers in. So we've got 6.67 times 10 to the minus 11. We're going to multiply by the mass of the Earth, 5.98 times 10 to the 24 kilograms, and then we're going to divide that by the radius, 6.78 times 10 to the 6, and we're going to square that. And that comes out as 8.7 newtons per kilogram. Okay, so the answer is 8.7 newtons per kilogram. So that's the field strength at that point. So it's still sizable. Okay, so the amount of mass that the International Space Station has, obviously there's still a weight to it. It's being pulled down towards the Earth. The reason why it orbits is because it's traveling fast enough so that it never quite reaches the surface. It follows that circular path. But it's still, there's still a weight. You feel weightless within the International Space Station, not because there is zero gravity. There is a gravitational field strength of 8.7 newtons per kilogram. It's just that you and the ship are both, the spacecraft are both, or satellite, are both falling to Earth at the same rate. So there's nothing kind of making that contact between you and the satellite, due to your weight. So you're always in a free fall, so you feel weightless, but you're not actually weightless. Right, next one. Okay, so next question we've got, this is our medium Earth orbit question. Okay, and these go from about 2,000 kilometers right up to 35,000 kilometers, which is just before we reach a geostationary orbit. And often these questions involve satellites like GPS satellites, and this question is about the Global Positioning Satellite, or a network of them. So we've got Global Positioning System, GPS, is a network of satellites orbiting the Earth. The satellites are arranged in 6 different orbital planes at a height of 20,200 kilometers above the Earth's surface. Wherever you are, at least 4 GPS satellites are visible at any time. The diagram shows a single satellite. Okay, so we've got our height above the Earth. And then here's the information we're given. It says that the GPS satellites take about 40,000 seconds, which is about 12 hours to complete one orbit. So that's our time period. And then we're given the mass of the Earth and the radius of the Earth. Bearing in mind again that we need to know how far it is from the center, but we've been given the height and we've been given the radius of planet Earth, so we have to add those two together to get r, just like the last question. And yet again, it's the same equation. We've got, so it's saying show that, so we have to get to this number or close to it. So we're going to use the same equation we did in the last question. And then this time, r is going to be the radius of the Earth, which is given as 6,400 kilometers in this question, and we're going to add to that the height above the surface of the Earth. Okay, that's 26,600 kilometers, so times 10 to the 3 meters above the Earth. Plugging numbers in, I've got 4 times pi squared times 2, I'll just put a 2.66 times 10 to the 1, 2, 3, 4, 7, and then we have to cube that, and then we're going to divide by 6.67 times 10 to the minus 11 times 6 times 10 to the 24 kilograms. And this question, it's 6, before it was 5.98. Just be aware of what they give you. And then we're going to square root that. And when you put all that into a calculator, it does come out as about 43,000 seconds, okay, which is pretty close to our 40,000 seconds. And if you divide by 60 just to get it into minutes, and 60 again to get it into hours, it does come out as about 12 hours. Okay, so a GPS satellite is orbiting the Earth at this distance, and it takes about 12 hours to orbit. Right, next question then. So This question is our geostationary satellite question. And this is going to be further than 35,000, so approximately that, just over. And remember the difference between geostationary and geosynchronous. They're both 24-hour time period, but for stationary it's because it's orbiting the equator, so it remains at the same position above the Earth at all time. Right, so let's read the question. Figure 2.1 shows an aeroplane flying in a horizontal circle at constant speed. The weight of the aeroplane, W, is the weight vertically down, and L is the lift force acting in this direction at an angle, a right angle to the wings. It says, explain how the lift force L maintains the aeroplane flying in a horizontal circle. Okay, so if we looked like down over this, then there's the center of the circle, and this would be the plane, and it would be going, oh, that's not very circular, be going around in a circle. Okay, and what we're suggesting is, what is the centripetal force, or what is the why does the lift provide that? And what we've got to look at here is breaking up this this force into components. It's got a vertical and a horizontal component. So the vertical component of the lift is obviously equal to the weight, so that's balanced vertically. And then the horizontal component of the lift, that's obviously our force causing it to move in a circle. So the horizontal component provides centripetal force, and the vertical component of the lift, that's balancing the weight. Okay, just a little question then on circular motion before heading into the orbit question, although we do have another part to this. Now obviously we're not really doing a circular motion question, but this one's still carry on with circular motion. I want to get to the actual satellite question, but we'll answer this. So it says there is a mass of 1.2 times 10 to the 5 kilograms, that's the airplane's mass, flying in a horizontal circle, a circle of radius 2 kilometers, so times 10 to the 3 meters. Centripetal force acting on the airplane is 1.8 times 10 to the 6 newtons. Calculate the speed. Okay, well, centripetal acceleration v squared over r, and so the force causing that, mass times acceleration, mv squared over r. We are calculating the velocity, the speed, so we're going to rearrange that. So our speed should be the force times the radius that it's going in that circle, divided by the mass, and the square root of that. And then put those numbers in, 1.8 times 10 to the 6 times 2 times 10 to the 3 divided by 1.2 times 10 to the 5, and then the square root of that comes out about 178 meters per second. Okay, right, satellite question. So figure 2.2 shows a satellite orbiting the Earth at a constant speed v. The radius of the orbit r. So it's given us the radius, it's not given us the height above, just giving us directly the radius to the centre of the Earth. It's also given our expression, so we didn't need to remember that. Remember that comes from looking at the centripetal acceleration, or the centripetal force, and that force is the force, the gravitational force between two masses. You make them equal each other, and then you rearrange for t, and we know that t is just dependent upon r and the mass of the planet. And what it's saying is show that, okay? So this question, it's not giving it to do a calculation, it's saying show this. So we're just going to do exactly what I've just suggested. So we've got, there's our planet, there's the satellite orbiting, travelling at some velocity v, little mass m, big mass of planet, the radius of the orbit r. It is travelling at that speed v because it is covering this distance, the circle's circumference, in that time. One orbit, one rotation is the time period, and we know that the centripetal force causing that, okay, is gmm over r squared. It's the force between the masses, separated by the distance squared, times by the gravitational constant, and that is equal to mv squared over r. Okay, so v squared over r is centripetal acceleration times the mass will give you the centripetal force, and that's equal to, so that is where the force comes from, the force between the two masses. Cancel the m's, cancel one of the r's, and then we've got this term, v squared equals gm over r, and now what we're going to do is we're going to replace the v in terms of t. So if I square this, what I'm going to get is I'm going to get 4 pi squared r squared, 4 pi squared r squared over t squared. That's going to equal gm over r. And then to finish off, I'm going to bring t up, I'm going to bring gm down, I'm going to bring r up to get r cubed, and I'll finish up with this expression. Okay, so t squared would equal 4 pi squared r cubed over gm. So there we go. We've shown that t squared equals 4 pi squared r cubed over gm. Okay, C. The satellites used in television communication systems are usually placed in geostationary orbits. In your answer, you should use appropriate technical words spelled correctly. State 2 features of geostationary orbits. Okay, very straightforward. So the time period is 24 hours. Okay, as it is for any geosynchronous satellite, but for it to be geostationary, static, above that same point, above the Earth, then it needs to be orbiting the equator. So, equatorial orbit. Good. Final part. Okay, so now it says calculate the radius of the orbit of a geostationary satellite. Okay, so we're going to find out how far above the center of the Earth it is. Okay, so calculate the radius of the orbit, and we can use this equation, but we need to rearrange this for r, the radius. So I would have t squared gm, then I'd divide by 4 pi squared, and then I need to find the cube root, and that's going to give me the radius of the orbit. Okay, putting numbers in. So we do have the mass of the Earth, we know g, we know 4 pi squared. T, the time period, well, that's 24 hours. We just need to convert that into seconds. So if t is 24 hours, then 24 times 60 to get into minutes, times 60 to get into seconds, that would be 86,400 seconds. So we now have t. So putting the numbers in, we've got 86,400. We need to square that. We need to times that by 6.67 times 10 to the minus 11. We need to times that by 6 times 10 to the 24, which is the mass of the Earth, and then we need to divide that by 4 times pi squared. And the final thing is to find the cube root of that, and that will give us the radius of the orbit of a geostationary satellite. So once you've put all those numbers in your calculator, it does come out at 4.2 times 10 to the 7 meters. Okay, so 4.2 times 10 to the 7 meters. And if this question was to say how high above the Earth is it, then you'd need to take the radius of the Earth away, which is 6.4 times 10 to the 6 meters away. So you'd have to remove that from there to get the height that the satellite is above the surface of the Earth. So just be careful with the question. Is it asking for the radius of the orbit, or is it asking for the height above the Earth? Right, final question. Okay, so this is a geosynchronous, okay, although very similar to the last question in terms of its 24-hour period. But this is going to be a question, a geosynchronous. Okay, a geosynchronous satellite. Okay, let's read. Figure 1 shows the orbits of two Earth satellites, a communication satellite in a geosynchronous orbit and a monitoring satellite in a low orbit that passes over the poles. So you've got this low polar orbit as well. It says that the time period t for any satellite in a circular orbit around a planet is proportional to r to the power 3 over 2. We discussed this before. The theory is that the time period squared is proportional to r cubed, and what we've done is just square root, just said it's proportional to r to the power 3 over 2. Okay, so that's correct. Where r is the radius of the orbit measured from the centre of the planet. For a satellite in a low orbit that passes over the poles of the Earth, t is 105 minutes. Okay, so the time period for this low polar orbit is 105 minutes. And that is where it is 7,370 kilometers from the center of the Earth. Now it says calculate the height, so it's actually asking for the height above the surface of the Earth in kilometers of a satellite in a geosynchronous circular orbit. Give your answer to an appropriate number of significant figures. Right, so we are going to, and they've highlighted this, they've given us this this proportionality rule, and what we can actually do is we can look at a ratio of the time periods between the two satellites, comparing it to the ratio of their the radius of their orbits cubed. So what I mean is, if I suggest, let's say that T1, okay, is going to be the time period for our communication satellite, and T2 is going to be the time period for our low polar orbit satellite, the ratio of both those squared should be equal to the radius of orbit for the communication satellite divided by the radius of orbit for the polar orbit cubed. Okay, and that's because if I do find t squared over r cubed, that should equal a constant. Okay, and that constant, bearing in mind we're talking about this expression, what we're suggesting is the constant would be, so t squared over r cubed should equal 4 pi squared over gm. And we're calling that a constant because of the fact that we're talking about these satellites above a specific planet that's not going to change its mass. 4 pi squared is a constant, g is a constant, so the ratio of t squared over r cubed is a constant, and then that means that the constant is the same for this satellite as it is for this satellite, so we can look at the ratios of these values. Anyway, why would we do that? It would simplify things because we wouldn't have to plug all numbers into all this to get out a certain time period and then plug it back into another equation to get out r. Okay, so let's just make this clearer. T1, we know that's 24 hours. Okay, in the last question we worked out in seconds how long that was. However, in this question I'm going to convert that to minutes, because as a ratio, if I just keep the time periods in the same units, they'll cancel. So I'm going to turn this into minutes, so 24 hours times 60, that's going to be 1,440 minutes. So that's the time period for the communication satellite. The time period for the polar orbiting satellite is 105 minutes. And then we know R2, that's the radius for the orbit for the polar satellite, that's 7,370 kilometers. And notice they want it in kilometers, so if we keep our radius in kilometers, we'll get an answer out in kilometers. And the only thing we don't know is R1, the radius that the communication satellite's going around the planet. So I need to rearrange this because I want to find R1. So R1 would equal T1 squared times R2 cubed, so I'm cubing that and bringing it over here, divided by T2 squared, and then I would need to find the cube root of all that to get R1. So here are the numbers. So we've got 1,440 squared times 7,370 cubed, divided by 105 squared, and then the cube root of that. Now that comes out as 4.2 times 10 to the 4 kilometers. However, that's the entire radius to the center of the planet. Okay, it wants us to find out the height above the surface. Now, as discussed in a previous question, where I just said that if you wanted to find out the height, not the radius of the orbit, but the height above the planet, you just have to take away the radius of the planet, and the radius of the planet Earth 6.4 times 10 to the 6 meters. So to actually find the height above, we're going to do 4.2 times 10 to the 4 kilometers, and we're going to minus 6.4 times 10 to the 3 kilometers. Okay, so that's the radius of the planet in kilometers. And it comes out as 3.6 times 10 to the 4 kilometers. That's the answer. The height that the geosynchronous satellite is going around the planet is a height of 3.6 times 10 to the 4 kilometers.